Okay, we're going to continue with class 18 and go through examples. So here's the example 5.3 from Borgnacki. And so we have this heat engine and we're producing power from this. So, as opposed to having a heat pump, and this is, let's see, so that it receives a heat rate right here of 1 megawatt at 550 degrees Celsius and rejects temperature energy to the ambient of 300 degree Kelvin. So down here. And there's 450 kilowatts that gets produced. We would like to know how much energy is discarded to the ambient surroundings and the engine efficiency and compare these to a Carnot efficiency. All right, so what we're assuming is that this is going to be a real engine. And so the high heat transfer rate, 1,000 kilowatts, and the work out is going to be 450 kilowatts. Now we don't need to do much for this. We just use the conservation of energy and write out that 0 is equal to, well, usually we write this, I'll write it as in right here, but we also want to have the net, so we have to minus the Q out. And then we also have minus the work out, or power out, because it's rate. So 0 equals 1,000 minus Q out, which we could call QL, by the way. And they're calling it QL, so maybe we should have called the QL right here. I should have wrote that. It was QH, this would be QL, and then this would just be W dot right here. But minus 450, and so simply this is a Q out, which we will call QL, sure, equal to 550 math. So we want the thermal efficiency, and that's just going to be W dot over Q dot in, right? So 450 divided by 1,000, we could do that math and we get 45%. You could have also, by the way, we will often write this right here, thermal, and go 1 minus, it's called QL, or Q dot L, or Q dot H, right? And so we go 1 minus 550 over 1,000, right? And you'll get the same thing. But just want to remind you that, same concepts, just this is a sort of a matter of convenience because of this up here. We're going at the Carnot now. And the Carnot can be found from the temperatures. 1 minus the TL over TH. Remember, they both need to be Kelvin. For whatever reason, they gave one of them in Kelvin, but the other in. So this was 300 Kelvin. They gave that in Kelvin, but the other was 550 degrees Celsius. So we need 273 with that. And so the 273, we end up getting 63.5% is the efficiency. So here's the real, and here's the fake. Not fake, but the ideal. So here's the ideal because of the temperature, right? That's just like, okay, because of these two temperatures, here's what's possible for a totally reverse cycle engine, which is what the Carnot is. But here is what we've measured for the real thing. And let's see. Also note, all right, so sometimes we might want to, in other sets of circumstances, find out how much work could be made with that 1,000 heat. So this is like something that we're able to produce. So like how much Carnot work could we have gotten? So here's our Carnot work, or Carnot power. Well, we would have taken our efficiency, our Carnot efficiency, and multiplied it by our high right here, right? So this is the amount that we would have been able to get out. So we go 0.635, and It's obvious because it's easy numbers right here. But that the possible is 635 kilowatts, obviously. This is compared to what we could have gotten to what we actually did get, which was 450. It's a short video. We could go into the next one. Sure. And the next one's actually the next several are kind of short. No, let's go. Yeah, let's go ahead and do this one. All right. I'm tired. I don't need to upload anymore. More videos. More is also better. All right. So here's the example of 5.4. Right. So we have an air conditioning unit right here, and as one mode of operation of an air conditioner is the cooling of a room on a hot day. It works as a refrigerator, shown down there. A total of 4 kilowatts should be removed from the room, right? So we want to get 4 kilowatts of energy out to the outside temperature at 35 degrees right here. We would like to estimate the magnitude of the required work. To do this, we will not analyze the process inside the refrigerator, but instead look as we did. I guess will be deferred to Chapter 9, but we will give a lower temperature limit to the rate of work, assuming it is a Carnot cycle refrigerator. So the equations that we'll use out of the book for a real refrigerator, we have a coefficient of performance for a refrigerator is, which is also called beta in this book. They call it as beta. Is going to be QL, because that's the thing we want. We want to remove heat this way and divide it by the work that it takes to get this. And we know that we get QL over QH minus QL, in case I need that. But we can also have the Carnot right here. So the COP refrigerator Carnot, and we might want to call this beta Carnot, is going to be, we use a temperature scale, right? So it's a TL over TH minus TL, right there. So there's your coefficient of performance for a Carnot one, right? So this is going to be like this, the smallest amount or the largest coefficient of performance, I should say, that would be possible given these extremes of temperatures. And we know that there's the QL is going to be 4 kilowatts. So let's see how much work would be required if we had a Carnot type of refrigerator. So the COP are Carnot could be equal to the lower temperature is what do we say? It was 24 degrees, right? And so remember, they have to be absolute scale. So 273 plus the 24. And we're subtracting down here, so we don't actually have to add in the 273. We could just subtract them. It's going to go from 35 to 24, right? Because you could add 273 to both of these and just go away. So we get a very large number. But that's the possibility, right? Is to have a coefficient of performance of that large. But now, if we want to find out, what they're asking is how much power is possible from this, or how much, what is the lowest amount of power? We could write that out back up to here, right? Because we could just equate these together, that one and that one. And we say, well, let's see what this is. So we're going to have the Q dot L divided by the coefficient of performance refrigerator Carnot, or 4 kilowatts divided by 27. You get 0.15 kilowatts, and what that is the smallest amount of power that would be possible, theoretically possible, in order to maintain this amount of heat removal given these temperature extremes. But one thing to keep in mind, this is just what the room temperature is, and so the room temperature is this, but the outside air is this. Notably, the coils here have to actually be lower than the air temperature, because heat needs to move from the hot to the cold right there, right? So this must be, from the hot to the cold, heat needs to come into there. So this room temperature, if it needs to be 24, this must be much less than 24, the surface temperature of this cooler, and also therefore the fluid inside here. And the same thing's true out here. This needs to be hotter than this, a higher temperature than this, in order for heat to be coming out right there. So even though these are the extremes of the room and the outside, we have that's a unnecessary thing for heat to be able to move. It has to have a temperature difference. So right there, we're already belying what that 0.15 kilowatts would be. So we'll go with another video, maybe two more, maybe one more for